learning approach. Firstly, we customize a 3D descriptor using principal axis descriptor, and that will describe the geometric characteristics of different types of equipment. Oh, by the way, in this study, we just focus on different classes of construction equipment. For example, dozers, excavators, trucks, and so on. And we use the descriptors to describe their geometry and train the classifier to build a model for the recognition. And we can collect the point cloud of the site in different ways, including the one I mentioned earlier, or just using terrestrial laser scanners, the commercially available scanners. And it'll go through a pre-processing step to downsample the point cloud, to segment the ground from the chunk of the point cloud, and apply clustering based on the principal axis of the clusters, and based on the Euclidean distance of different chunk of points. And when we have the processed point cloud, we can apply the 3D descriptor and use a classifier to identify or to recognize which class certain point cluster is. And I'll show you an example here. So this is the point cloud from the construction site. You can see it's very cluttered, and in the middle you have a excavator. So basically we use the ground erosion method to get rid of the ground. And then cluster the point into different boxes, using bounding boxes to represent its orientation. And because in this case we're categorizing construction equipment, so we know roughly their size, we apply a size filter to get rid of the irrelevant object in the scene, and then apply the classifier to identify which category this construction equipment belongs to. And here is another data set from a equipment yard. Here we have 5 classes, and we apply the same method to identify their classes. Okay, so this is slightly different from the previous two. This one is very specific about crane lifting. So crane is very important. Crane lifting is a very important activity on site, and the safety has been criticized for a long time, and it will lead to very serious accidents. So it's important to provide real-time assistance to the operator to help him or her operate more safely and efficiently. So in this project, the first part is to model the dynamic workspace. We use a similar method to collect the point cloud data in the beginning of the day. And then in real time, we use computer vision to track mobile objects in the workspace of the crane and update their location in the point cloud. Because, well, the assumption here is they're always on the surface. So we can capture the dynamics in the crane workspace. And then we instrument the crane with sensors to get its rotation and extension of its parts, so that we can reconstruct the crane motion in real time. And finally, this visualization is presented to the operator in real time. And because we have everything in the program, we can set safety rules for proximity, for overloading, and give warning to the operator if needed. And we apply the same approach to another scenario. This is a crane on an offshore platform. And they have very stringent requirements for safety. And as you can tell, there are a lot of blind lift on the platform because of the obstruction of the structure. So they want to give the operator another layer of assistance in addition to the signal person or the signal person. So we were installing the system and testing system on one of their offshore platforms. Okay, so that's some projects I did in the past. And I don't have a conclusion slide, but instead I want to talk about what are the future topics that I'm interested in terms of robotics in construction. So first, design for robotic fabrication and assembly, because current